The ERFC function returns the complementary Gauss error function of a value. In this video, we will show the expansion of the ERFC using the Taylor series, Taylor-Maclaurin series sum, and regress it using LINEST Polynomial Regression. Let's generate the ERFC function using array formula. ERFC the x values. Here you have the trend line of the ERFC over values of -2 to +2 for x. And here you have the trend line equation to the degree 6, and you'll notice the r square is 1, meaning it's a perfect fit. We can get this same value using the ERF function. First, we enter the ERF function, the dataset of ERF, array formula, ERF of the x values. So in red, you have the ERF values. The formula to get the value of ERFC is 1 minus ERF. So we add 1 minus ERF to the formula. 1 minus, change the formula to 1 minus ERF. Now we have the exact same value of the 1 minus ERF. We can use these same values or generate an approximation of these values using the Taylor-Maclaurin series sum, where it is equal to 1 minus the Taylor-Maclaurin series sum of ERF, which is the summation of a times x to the 2n plus 1, where the values of n starts from 0 to infinity. In this case, we're limited only to our dataset, but it should continue to infinity. And we start calculating the formula. Enter the formula. So 1 array formula, 1 minus series sum of the x values where the x values increases from x to 2n plus 1, so n at 0, so that's 1, so x to the power 1 incremented by, so the next level will be n equals 1, 2n plus 1 is 3. 2 times 1, 2 times 2, 4, 5. So it increases by 2 to the n, to x to the power 1, x to the power 3, x to the power 5, x to the power 7. So 1, 3, 5, 7. The interval there is 2. And our coefficient will be this range. Now let's work on the coefficients. We begin with the denominator, which is array formula of 1 over 1 factorial. So factorial of the n values. That's the denominator part. So there are 3 parts in the denominator. We'll add 2 more parts. So this will be the second part will be 2n plus 1. 2 times n plus 1. This is the second part. After 2n plus 1, so let's see how it works. So we can add the third part times square root of pi. So we have 2n plus 1. Now we can work on the numerator. To the power minus 1 to the power n. We're almost there. We take the last part, that is 2 times. Now we're finally there. So the yellow covers the red and the blue data set. So here you have the value, the approximation is almost the same as the actual values. At the center, at the mean, you have the approximation perfectly the same as the actual values. So they are exactly the same here in the areas between -1 and +1. Next, we will calculate these coefficients because you have coefficients b1, b2, b3. There's a slight difference in b2 and b4. There's now some differences in b4 and b5, b6. We calculate these regression coefficients and compare this with the expansion coefficients. To do that, we will complete the 1 comma x matrix. So it will be x to the power 0, x squared, or x, that's x to the power 1, x squared, x cubed, until x to the power 6. So we enter the power. So transpose, or the power up to 6, because we're calculating up to the polynomial regression to level 6. So this is array formula of the x values raised to the power, and this will be array formula. And we lock the references. Now we can drag. So you see the x column, which matches to our x values. The x squared column, x cubed, and so on. Now that we have the 1 comma x matrix, we can use the LINEST array formula. No, this is LINEST. LINEST of the ERFC column, data y and data x. Second, the red one, we have LINEST, data y, and data x. And the third will be the expansion, the Taylor-Maclaurin series expansion of ERFC. So LINEST, data y, and data x. Now let's compare the regression. So RB0, all of them are 1. RB1, negative 1.08. They're all negative, rather was negative 1.09. RB2 is 0. That's because negative 1.34 times 10 to the minus 16 is very small, small enough to be 0. Negative 1.11 times 10 to the minus 16 and negative 9 times 10 to the minus 18, they're small enough to be 0. B3 is negative 0.26 or positive 0.26, 0.26, 0.26, and 0.27. B4, 0. This is 5.5 times 10 to the minus 17 exponent times 10 to the minus, that's small enough to be 0. Negative 2.84 times 10 to the minus 17. All these are times 10 to the minus 17. They are small enough to be 0. B5. B5 is 0.0289. There's a slight difference, 0.034. And B6. Negative 5.44 times 10 to the minus 18 times 10 to the minus 21 times 10 to the minus 18. They're too small, small enough to be 0. This completes the uh, LINEST Polynomial Regression of ERFC and the Taylor Maclaurin SERIESSUM expansion of ERFC.